So in this video I cover uh, need of excitation. So why the excitation is required for alternator, I will discuss clearly. So first of all, what is the need, and then what are the types of excitation. These are the types of excitations, and I will explain all those things. And first of all, what is the need, why we need to use this excitation. And this excitation is electromagnetic. This excitation is electromagnetic excitation. If we use electromagnetic excitation, we can controlling is possible. Controlling is possible. If you use permanent magnets excitation, it's very difficult to control the some parameters. So first of all, this first point is as adjust the excitation current. Excitation current, nothing but field current. Field current according to the change of generator load to maintain the terminal voltage as a given value or constant. For example, if the load voltage is load should maintain 230 volts or 4 or 40 volts. For load voltage, if the loads are increasing, the load voltage will be decreases, and this 230 also decreases to 190, like that. I think, but if the load value is decreases, and we should change the excitation current, we need to increase the excitation current. If the loads are decreasing, then voltage will be increasing. So that we need to decrease the field current. Simply, if the load voltage decreases, we need to increase the excitation current, so that it will compensate the whatever the drop which is available. And the next one is the most important one, parallel operation. In the control of a parallel operation is reactive power. Reactive power distributed between the generator. For example, if the two alternators are connected in parallel. So between these two, load shared, load shared, load shared can be in terms of reactive power only. But if you adjust the excitation current, if you adjust the field current, this reactive power will be controlled. Reactive power will be increases. If you increase the excitation current, the reactive power will be increases. If you decreases the field current, reactive power will be decreases. But in the parallel operation, if you control the field current, the two generators or any two of generators will share the load by compensating the reactive power. Nothing but, for example, this alternator, this alternator is available. For example, if the two alternators not sharing the load equally, then excitation will change. If the excitation changes, as per that one, the reactive power will be shared between the two alternators. Simply, this if you change the excitation current, reactive power control will be controlled, and that will be shared between the alternators equally. And the next one is improve the static stability of the parallel operation of the generator. Static stability is nothing but maintaining constant load, constant load or voltage. So to maintain constant load, constant voltage, that is nothing but static. Static is nothing but fixed. Dynamic is nothing but changing or moving. So that is for static stability. And also to improve the transient stability, for example, load on the alternator will be increases or decreases, or suddenly increases or suddenly decreases, or randomly changes. I think what these are the variables of load. So because of these variations, some fluctuations will be takes place. Those fluctuations are nothing but transient, transients. In your home also, if you turn on a load suddenly, for example, water heater, a geyser, a refrigerator, whatever it will be, huge load. If you turn on huge load, another load will get disturbed. Other load will get a disturbed, somewhat disturbance will take place. Such a disturbance is called transient. So nothing but that transient should not affect on the alternator. Sudden falling of the load, sudden rising of the load, some voltage variation will be takes place. Those transients, those variations can be improved. Nothing but variations or transients will be decreases with this excitation. And next one is when there is a fault inside the alternator and de-excitation is performed to reduce the degree of fault losses. Think but for example, if any the generator is available here, if a fault occur here, if you continuously excitation is available and it will generate electricity. Nothing but if the armature is having a huge current in the presence of field and rotation. So, for example, if fault occurs, the fault will be increases very fastly in the presence of field and rotation. So that but if you demagnetize the excitation, if you demagnetize the excitation, the EMF production in the alternator will be decreases. Then there is no current, so that the fault level will be decreases, improved, nothing but become less if you demagnetize the excitation. Okay, but these are the various types of benefits if you use variable excitation such as electromagnetic excitation. These are the need. First one is to maintain the voltage level, to change the reactive power as per the load, or to maintain the static stability, to maintain the transient stability, and to decrease the fault level, to decrease the degree of fault level. So for this all purpose, we are using the excitation, and there are different types of excitations are available. And as per our convenience, we are using different types of mobiles, different types of PCs, personal computers, different types of classifications are there. In the same way, excitation also based on capacity of motor. Capacity, for example, short capacity, medium capacity, large capacity of alternators are available for different types of alternators, and the different types of excitation will be used. So the types are sorry. So by using DC generator, so this is DC shunt generator, and this is placed on shaft of alternator. So the shaft is turbine is mechanically connected to the alternator through shaft, and on the shaft this DC shunt generator is used. So the DC shunt generator will produces the DC output, and which is this output of this one is connected to the field winding. So these are the poles are available like this. For this is field winding, and DC supply is available. I think DC supply is output of this generator is connected to the DC supply. This is by using DC generator, and the next one is static excitation. So static excitation, nothing but without as per load, it will control voltage without varying uh, load voltage. That's why this is called static excitation. And another one is brushless excitation. Brushless excitation. I think that there is no direct to brush. There is no brush to the nothing but by using DC generators and static excitation through brushes, we need to inject the supply to the alternator. This is through brushes we are giving the supply to the alternator rotor. But without brushes also there is excitation is there. This is used for high capacity. This is medium capacity. This is low capacity. This is mostly used in wind or non-renewable energy sources. So let us discuss one by one. First one is this is a DC uh, generator. This is very easy. So this is the field of DC generator, and the rotor of the DC generator. This is shaft is connected to the through shaft. It is connected. Okay, this one. This is a pilot excitation. This is pilot excitation. Actually, this is field of DC generator. This is DC generator actually, and this is also a generator. By using this generator, field current as a load, and by using this field, this generator is rotating, and it acts as a generator, and it will give the supply to the alternator field through brushes. Alternator, it will generate electricity in the form of DC, and which is connected to the brushes, and look at this one. This generator field is from another generator. So this field current IF is using another generator which is connected in shaft. So in this generator is suitable for low capacity. So this is split rings are available here, and the two split rings field field supply is given to the alternator, and you can see here there is no controlling of field current here, and there is no static control. There is no automatic control in this DC generator. This is mostly used in non-renewable energy sources, and also low capacity alternator. So this is one type. So another type is this is static excitation. This is a static excitation, which means look at this one. First, initially, the generator alternator will not produce any electricity. So first, this by using battery banks. I don't know, by DC batteries are available in the market. By using battery banks, DC is connected to the alternator field. This is field of the alternator, and also field flashing also is you can use. Field flashing is about giving the flux to the field winding, and if you give the flux, some flux will be available here, and you need to rotate this is at synchronous speed, and EMF will be produced at the terminals of the alternator, and the output of the alternator is available here. From this output, PTs and CTs, we can measure the voltage, or we can step down the voltage, and PT's voltage can be regulated by using the regulator. CT's current will be controlled by using the step down or step up transformer here, and here CT's PT's, we are maintaining constant voltage, and constant current. Constant voltage is PT's, constant current is using CT's. So this is given to the, look at this one, positive terminal to the field winding, and negative terminal to the another field winding. Positive terminal here, negative terminal here, which means after generating the electrical energy, after generating the electrical energy of the alternator, that energy is tapped back to the field winding by using the regulator, by using the uh, CTs and PTs, regulators and transformers. And you can see here thyristor bridge rectifier. So this is You can understand the power electronics subject in your fifth semester. By using this thyristor bridge control, we can get AC into pure form of DC. Nothing but this is also in type of rectifier, uh, but controlling is very smooth. Controlling is possible by using thyristor rectifier. Nothing but this is AC is available here. AC is available here. From AC to we will get a DC after the thyristor bridge. So this after the thyristor bridge that will be converted into DC is given to the field winding. For example, this thyristor will control the, so V is equal to Vm sine omega t or alpha. This alpha will changes from 0 to 180 degrees. So I think that if you want to turn on it 60 degrees, it will be turn on at 60 degrees or 70 degrees or 30 degrees or 50 degrees. But thyristor can be, the thyristor will produces the output based on the load demand. For example, if the load is required more reactive power or more voltage, thyristor should turn on at you can see here thyristors turn on at lower angles. So nothing but 10 degrees or 20 degrees or 30 degrees. So you will get the exact output, 30 degrees output or full output like that. Nothing but output can be controlled. Output can be controlled. Nothing but field current will be controlled by using the thyristor bridge rectifier. So I think that by controlling this one, we will give the generator alternator will produce a constant output. Such a constant output is possible with a constant field winding. That is called static. That constant is called static or static excitation. Simply here, first initially you need to give the small flash field to the field winding, and we need to at the time of rotating of the alternator, if you give the flash field, and alternator will cut that flash flux and it will produce the electricity, produces output. That output taken back to the field winding through the CGs and PTs and a regulator and transformer. And after the regulator and transformer, the thyristor bridge converter, which converts AC into DC because our field winding is required DC. That's why the thyristor bridge rectifier converts AC into DC, and the constant output voltage of alternator can be achieved by using the static excitation. Nothing but the bridge rectifier will give the controlled voltage, controlled field winding. Sorry, controlled field winding. This is all about static excitation. Next one is brushless excitation. This is also called pilot excitation. Pilot excitation. This is also a simple one, but in the absence of brushes, brushes are not available here. You can see this. Uh, so there are different parts are available. Main different parts available here. So here pilot excitation are stationary or rotating permanent magnet pole. So you can see here, for example, this is rotating at 500 rpm, 500 rpm rpm rotation per minute. So everything, this shaft is connected throughout the entire system. So this permanent magnet is available. If you rotate this one, this armature produces the EMF. And you can look at this one this way. This is in terms of AC. AC will be produces. AC will be converted into DC by using thyristor control to rectifier. You know very well about the rectifier, which will converts AC into pulsating DC. But in thyristor control rectifier, this off cycle also controlled. Nothing but in off cycle, small portion also will get it will transfer to output or full portion. That is nothing but this off cycle also will be controlled by using the this thyristor control rectifier. This by using permanent magnet AC will be generated in the armature, and then by using the converter, this is it will convert into DC. You can see here by using this is the field winding constant DC. Here armature is available, rotating armature is available. Here rotating armature is available here. This rotating armature will cut the field flux. This flux, it will cut the field flux. Again, it will produces the armature armature EMF and this induced AC of armature will be converted into, look at this one, this is a diode wheel rectifier. This rectifier will convert AC into DC. AC into DC. Look at this one. This DC is given to the field winding. DC is given directly given to the field winding. Nothing but this entire system, this field winding is rotating. This diode which wheel rectifier is rotating. Main field, this is rotating. This is my permanent magnet is rotating. Armature is rotating. Diode rectifier is rotating. Field also rotating. So everything is rotating. There is no need of placing the brushes to give the supply to the field winding. Directly you can give the supply. So here simply the system is here AC is generating by using the permanent magnet. It will convert AC into DC. This field, the DC field is given to the armature. This armature converts again, it will produce a AC. This AC will be controlled, or for example, if it is generating DC, no problem. This bridge diode will rectifier will convert pure form of DC. Otherwise, if it is generating AC, this diode will rectifier will convert into DC and it is given to the field winding. Here we are not using any brushes. That's why this is called brushless excitation. So field flux will be produces and it will rotate and it will rotate and again uh, it will cut the armature flux. It will produce three-phase alternating current. So that it will regulate by using the output voltage. For example, if your output voltage is 400 voltage and is 400 voltage is compared with the thyristor control rectifier. For example, here producing is 380 volts. Here is 400 volts. Nothing but look at this one. For example, here output is 400. Here is 380. So these two will be compared and the voltage will be improved by using the thyristor control rectifier. Nothing but here low voltage is available, then the field current will be increases by using the thyristor control rectifier. Here field flux will be increases. Here induced EMF increases, so that field current will be increases. So this is used for a high capacity alternators. So controlling is very sensitive. So this is all about the three different types of exciters used.